Hello my dear student. So in this video we are going to see data representation series, and this is the next video, and this video is based on binary representation of integer numbers. As we know, computers store data in the form of binary numbers, but we deal with the decimal numbers. So how these integers are stored in computers memory. Okay, so we'll move to the next slide and see. So the integer can be represented in various ways in computers. So there are basically three: sign and magnitude representation, ones complement, and the twos complement. So we will be looking at each one of them one by one. So in this video we are mainly focusing on sign and magnitude representation. So this is the conventional method, okay, to represent any number. So integers are identified by their sign. We know that it can be positive or negative, and followed by a series of strings of digit which represent its magnitude. For example, let's say plus 17 or 23. So normally what we do for positive number, we omit this sign as positive. It is understood. But for negative number, we need to use the negative sign before the number. Let's say 14, minus 14 or minus 15, or it can be any other number. So to represent sign of a number in the positive or negative, the leftmost bit, which is called the most significant bit, is used. So always remember to represent the number as positive or negative, while in the bit binary form, the leftmost, that is called most significant bit, is being used. And if it holds the value as 0, then it means positive number, and if it holds the number as 1, then it means it is negative number. So please remember, we'll always see the leftmost bit, which is called most significant bit. If it is positive, then 0 will be used, and if it is negative number, then 1 will be used. Let's say, for example, in a computer with the word size as 1 byte, that equals to 8 bit, how we are going to represent a particular number? Let's say, for example, plus 15. So as we know, this is a positive number. For positive number, we use 0. We use 0 as for the signed bit or most significant bit. So that is why we have mentioned 0 over here. And because out of the 8 bit, the 1 bit has been acquired by the signed bit, the leftmost or reserve, we can say. So rest of the 7 bits are for magnitude. So we know that 15, when we'll convert 15 to its binary form, it is 1111. So we'll start filling from right to the left. So it is 1111, and remaining bits will be filled with 0. Okay, so this is the way how we represent plus 15 in a 1 byte or 8-bit word size in a computer. Okay, now same way we are going to take another example. Let's say for minus 23. So because of it is minus or negative number, the leftmost bit, that is the most significant bit, now will be holding number as 1, because 1 represent negative. As we know that 1 represent negative number, and rest of the 7 bits are for magnitude. And we know that 23, if we convert 23 to its binary equivalent, it is 10111. So we have started filling these ones 11101. Okay, and remaining 2 bits will be filled with 0. So this is how we will represent 23 in 8-bit word size computer. Okay, so this point need to be noted, that the leftmost or the most significant bit is always reserved for signed. So that is why it is also called signed bits. 0 for positive and 1 for negative. Now move to the next. Okay, Now, the total number which can be represented by n bit word size for a sign and magnitude representation, the formula is 2 raised to power n minus 1. So, total number but which we can represent for a n bit word size, how we can compute by this formula 2 raised to power n minus 1. Whereas for a binary word size of 8 bit, the most significant bit, as we already know, is reserved for sign notation. So that is why maximum magnitude can be represented using how many bits? 7, because 1 out of 8, 1 is reserved for sign. Okay, so let's take few examples. So maximum number which can be represented in 8 bit sign notation is, because out of the 8, the 1 is reserved for sign, the leftmost, that is most significant. So how many bits are left now? 7. So the maximum number which we can represent is 2 raised to power 7, that is 128. Okay, or you can say the magnitude. But an 8 bit word can represent how many total numbers? That is 2 raised to power 8 minus 1, because of this formula 2 raised to power n minus 1. So in this case it is 2 raised to power 8 minus 1, that is 255. So 255 numbers can be represented, and they are ranging from minus 127 to 0, and then from 0 to plus 128. Okay, so this is the range. Within this range, a number can be stored in 8 bit word size. Okay, say let's take an example, another example, like maximum number which can be represented in now 16 bit. So that is quite simple. Out of 16 bit, 1 is again reserved, that is the most significant bit. So remaining bits are 15. So 2 raised to power 15, that is 32,768. So now with the 16 bit word size, we can represent 32,768, whereas with the 8 bit size we can only represent 128 bits. Okay, so in this case 16 bit word can be represented. So total how many numbers? That is 2 raised to power n minus 1 again. So in this case it is 2 raised to power 16 minus 1, that is 65,535 numbers, again ranging from minus 32,767 to 0, and then 0 to 32 plus 32,768. Okay, so this is the range for 16 bit, whereas this is the range for 8 bit. So this way it goes up. So we are keeping this video till here only, and in next video we will discuss about 1s and 2s complement. Thank you very much.